These PowerPoints are very long, so I edited this one down for myself by email, but for some reason I was having trouble accessing it yesterday morning. But that's what we talked about. Now this is instantaneous induced dipole interactions here. Normally this is time average. In one instant of time you might have a dipole that looks like that. Here's some data. I guess I showed this, you know. As the number of electrons increases, the boiling point increases because the dispersion forces will increase in this particular place. All these molecules are nonpolar. We talked about shape. You know, this is that sphere I drew. Both of these have the exact same number of electrons.
The linear one has a...
Yeah, the linear one has a much higher boiling point. The boiling point is 36.1 degrees C. This is only 9.5 degrees C. So neopentane is a gas, actually, at room temperature, whereas pentane is liquid. So let's go with the slideshow.
So in a linear one, the longer dispersion forces are strong.
Yeah, more surface area. Dipole interactions with permanent dipoles. This chart you just have a rough idea. You don't have to know the trends exactly. Hydrogen bonds are unusually strong. We're trying to show this using the electrostatic potential map here, but it's hard to see because it looks like this proton here is pretty well shielded by electron density, but it's not, and so it's almost a full positive. Maximizing hydrogen bonding interactions. This is called a molecular solid. Molecular solids, you know, consist of molecules held together in the solid state. So what holds together molecules? Intermolecular forces. In general, intermolecular forces are weak, and so molecular solids typically have low melting point, are soft, they don't conduct electricity very well, and so something like ice, you know, it's soft, it's easy to crush. And that is, you can break these intermolecular attractions without too much difficulty. Molecular solids, yeah, it's recording. Molecular solids have low. Compared to what kind of solids? Compared to ionic solids? Ionic solids are fairly high. If you try to melt ice versus melting table salt, there's a huge difference in temperature. It's because the bonds, you know, ionic bonds versus intermolecular forces, no comparison in that case. You know, ionic bonds are going to be much stronger. If you try to melt aluminum oxide, you know, you aren't going to be successful. This stuff has such an extremely high melting point. The bonds are so strong. But you could also have covalent network solids. Can you give me an example of a covalent network solid? Diamond. Have you ever tried to melt diamond? No, the bonds are very strong. You know, it's going to be difficult. And so, covalent solids are you know, covalent solids, especially like diamond. Diamond's all sp3 carbons with sp3 sigma bonds. Those are very directional. So if you try to break it, you know, you're going to disturb the overlap. There's going to be one part. And so in order to break it, you got to break those bonds. Whereas something like sodium chloride, you know, each sodium is surrounded by 6 chlorides, each chloride surrounded by 6 sodiums. So in order to displace it a little bit, it's not so difficult. Because ionic bonding is what they call non-directional. Non-directional in the sense that, you know, the ions just try to pack in such a way that they're surrounded by oppositely charged ions, you know. But there's no particular direction, like there's no tetrahedral, you know, angle or fixed tetrahedral angle, because there's no hybrid orbitals where, you know, if you distort the angle a little bit, you got to break the bond. Metals are like that too. Metals are non-directional bonding, so metals are malleable. You know, you can displace the atoms without too much difficulty because it doesn't break the bond. This is an example of a dimer. You know, when you have those two strong hydrogen bonding interactions. The more hydrogen bonding interactions, has a boiling point. And so we looked at these, surface tension, adhesive versus cohesive forces, meniscus, right? We looked at the enthalpy of vaporization. Things with strong intermolecular forces are going to have strong or high enthalpies of vaporization. We looked at the vapor pressure process. The vapor pressure technically is when we reach this sort of dynamic equilibrium.
The pressure
Yeah, where the pressure
equalizes.
equalizes. It's constant, but the molecules are cycling, in and out of the liquid phase. Because there's constant evaporation, you can't stop it, and there's constant condensation. It's just that the evaporation rate is equal to the condensation rate. So that's going to give you a fixed amount of humidity. That's 100% humidity right there. If we're less than 100%, then we're going to have net evaporation. This is measuring vapor pressure. Measuring vapor pressure, we get vapor pressure curves like this. Vapor pressure increases exponentially with temperature. Easiest seen not in the data table, not in the graph, but in the form of Clausius-Clapeyron equation I gave earlier. This is the boiling process. What happens is, does temperature change when you boil water?
Eventually.
Not during boiling. During boiling, all the energy is used to vaporize the molecules. And so the energy is not being used to heat it up. It's being used to break apart the molecules to get them in the gaseous phase. That's the reason why the temperature here in the cup, this is a paper cup with water in there, the temperature here is stable at 100. At 100 degrees C, the cup is not going to burn. And so the water, okay, once all the water has vaporized, then we're heating an object. And so this is a process here where the temperature stays constant. The temperature of the water and the temperature of the steam, both at 100 degrees C, in this case 99.9. Here's where the water is completely vaporized. Now the object is just going to heat up. This is amount times C times delta T. This is amount times delta H of vaporization. And the delta H of vaporization for water is kind of high at 44 kilojoules per mole. That high vaporization is important. Some people are asking about regulating body temperature. One way you could do that is by evaporating sweat. Because the high enthalpy of vaporization has a good cooling effect on your body. Unless, of course, it's 100% relative humidity. If it's 100% relative humidity, are you going to be vaporizing much? No. It's going to be uncomfortable because you're going to be vaporizing and it's going to be condensing at the same rate. So it's cooling and heating, and so the net change in temperature is nothing. Here, this is kind of interesting because this is water boiling at room temperature. Can water boil at room temperature? Yeah. What you have to do is you have to suck on this and create a vacuum here. And so how much vacuum do you need to get water to boil at room temperature? Well, we could use the Clausius-Clapeyron equation, or we could just go here and look. We have to reduce the atmospheric pressure to 23.8 millimeters of mercury. If we can reduce it to 23.8, then the vapor pressure water is equal to the atmospheric pressure, 23.8, and boiling spontaneously occurs.
Without heat?
Without heat, right. Yeah.
Wow.
Well, the heat's there, it's room temperature.
That's crazy.
We don't have a strong enough vacuum pump here. I think in physics they do, but I tried it on this vacuum, but
Can you do it?
it's not very impressive because you have to heat it a little bit. You don't have to heat it to 100 degrees C, but our vacuum is like hundreds of millimeters of mercury. And so then the effect isn't as impressive. Okay, well, going from a liquid to a gas is called vaporization, but a liquid can also go directly to what we call supercritical fluid. And what happens with a supercritical fluid is you have a certain pressure. If you meet the pressure and the temperature requirements, what phase you get is something, it's not a liquid, it's not a gas, it's not a solid, it's a supercritical fluid. And what is a supercritical fluid? When you watch this occur, what happens is this liquid just expands to fill the volume of the container. It's really weird, but it's still like a liquid here because it's quite dense. It's not like a gas. And so it has properties of both a liquid and a gas. But you have to be at T sub C and P sub C. P is the critical pressure. T is the critical temperature. And so once you hit that, then you can generate this unusual state of matter. Not everything generates this, but that's a supercritical fluid. The liquid just expands to fill the volume of the container. So it's weird. Here are some
uses.
I'm sorry?
The uses of
The uses of supercritical fluids, decaffeinating coffee beans, you know, dry cleaning, with like CO2 is nonpolar, so if you have dirt, grease, you know, the supercritical CO2 is like washing it, and then you release the pressure and it just evaporates completely. But there are a lot of uses. In fact, there's some videos showing some of the uses, animations that I don't have time to show up, but you should look them up if you're interested in these. Well, what kind of conditions do you need? For example, CO2, you have to heat it to 304.2. Is that hard to do? No, that's very low temperature. That's lower than the boiling point of water, which is 373. But you have to increase the pressure to 72.9 atmospheres. Is that hard to do? Yeah, that's hard to do because you need a stainless steel chamber, like a bomb, you know, to contain it. In fact, if you look at all these pressures, tens to hundreds of atmospheres of pressure to get a supercritical fluid. But it's just an interesting state of matter. All right, this is called a temperature and time scale, or temperature and Q scale. Usually I like to go with Q because what happens is you cool it down. As you cool down a liquid, it should hit the freezing point. This is water. So water cools down. Does water cool down linearly or exponentially? Exponentially. It slows down as it gets closer to the ambient temperature. Well, anyway, water cools down, and then you hit the freezing point, and then it stops cooling down. Now, all the energy you're removing, you're still cooling it down. You're still removing heat. Well, all that heat you're removing goes into freezing the liquid, and the temperature remains constant. Once you've solidified all that liquid, then you're cooling the solid. And so this is object cools, liquid cools. This is amount times C times delta E. This is freezing, which is a process. This is amount times delta H. And then this is cooling of the solid, amount times C times delta T. And so some calculations, what you have to do is you separate it into three separate calculations, or you do it as one combined calculation. So let's say I wanted to figure out how much energy, how much heat do I have to remove to cool, let's say, a liter of water from 100 degrees C to a solid block of ice at minus 40 degrees C. Now, how much heat's required? Well, what you have to do is you have to do three separate calculations and add them up. Right? You do Q1, Q2, and Q3 for each step, because they're different. System is an object, system is a process, system is an object, solid block of ice. So those are calorie. This is, on the other hand, is the heating curve. This is a cooling curve. This is a heating curve. And again, I like to use Q instead of time, because as Q increases, what's going to happen to a solid? The solid is going to warm up. Right? As Q increases, the solid warms up. Q is equal to the amount times C times delta T. So we need to know the specific heat of the solid until we get to the melting point. This is water, ice. So we heat up the block of ice from sub-zero to 0. When we hit 0, what happens? As we add heat, the temperature doesn't go up. As we add heat, we melt it. So this is a process. Q is the amount of heat required for this step is amount times delta H of fusion, vaporization, condensation, fusion for melting. Once we've melted all of it, then we're just heating an object, which is liquid water. And so as we had heat here, Q is equal to the amount times C times delta T.
Why the graph is linear?
Why is the graph linear for the heating? It's just heating linearly. Whereas cooling is just, it's releasing heat. This can be more linear because you're putting a hot plate under there, you know, rather than cooling to the surroundings. And how fast it cools depends on the temperature difference between the surroundings and the system, whereas how fast it heats just depends on the temperature difference between your heater and the object here. So that you can have more control over. This is, do you see this overshoot here? The overshoot is because when water crystallizes to form the solid, all the water molecules have to align perfectly to form an ice crystal. And so in order to get that alignment, let's see. In order to get that alignment, you know, it's not so easy, right? There's kinetic energy, and you're slowing things down, and this water has to pop into alignment here, and this water has to pop into alignment. And when they're all lined up perfectly, then a crystal of ice forms. This lining up process is called nucleation. You know, you nucleate crystals. And then as the nucleated crystals grow, then we get bigger and bigger crystals. And so sometimes, you know, nucleation is difficult because, you know, what's the first water molecule to nucleate? And where does that first water molecule go in nucleation? And so this is what happens. For crystals that are hard to nucleate, they're sluggish to crystallize, so you can supercool them. They aren't stable, they're supercooled liquids. But it's just sluggish to nucleize because the orientation has to be just right for the crystal to form. You can prevent this by adding seed crystals here to help the nucleation process. Or some substances nucleate quite rapidly, like liquid metals. No problem, those crystallize rapidly. There's no sluggishness to that. But things that require orientation or big molecules, those are often sluggish to crystallize. Here's some enthalpies of fusion. Fusion, enthalpies of fusion, of course, are going to depend on the strength of the intermolecular attraction or the bond. You know, these melting points are all very low because what you're breaking are intermolecular forces, IMFs. Whereas diamond would have a huge melting point. Salt, table salt, has a huge melting point. Another process can occur, and that is you can skip the liquid phase altogether and go straight to the gaseous phase. That happens with iodine under normal conditions. Iodine doesn't melt, it just vaporizes or sublimes. CO2, dry ice, is another example. Does that melt under normal? No. It just vaporizes. Is there some kind of organic smell in here? What's it coming from? Was that door open earlier?
We're not supposed to smell it.
No, I mean, it's not good to be breathing in some vapors.
Is there a reason why you can superheat water within like above 100? Is that as well? It's the same thing.
Yeah, exactly. It's the same thing because bubbles have to nucleate also. And so if you have superheated water and you add some like pellets in there, you're going to get what they call a bump or steam kind of explosion. And so, yeah, it's because bubbles are slow to form. And so that's why, to prevent superheating water, which is always a problem, especially with smooth beakers, we add things called boiling chips to the water. The boiling chips are just quartz crystals that have lots of corners and nooks and edges so that bubbles can form more easily. And so that promotes smooth boiling at 100, because superheating is kind of dangerous times. Well, this is a phase diagram. Here we could see something like CO2, or iodine. Iodine under 1 atmosphere here. Actually, iodine should melt at 1 atmosphere. Because here, if the pressure is 1 atmosphere and I increase the temperature, I go from solid iodine to liquid iodine to gaseous iodine. And so this is the melting line here. This is the vaporization. In fact, this curve here is called the vapor pressure curve of the liquid. This tells us the boiling point. This C stands for the critical point, where we have the critical pressure and the critical temperature. And up here we have the mix between a liquid and a gas, which is called the supercritical fluid. At lower pressures, iodine doesn't melt. At pressures down here, we go straight from the solid to the gas. So this would be the sublimation curve here. And so we have sublimation, melting, vaporization. And we just use this to figure out what the most stable phase, or what kind of phase changes are we going to experience for different substances. And so carbon dioxide, will carbon dioxide ever melt into a liquid? The answer is yes. At 1 atmosphere it won't. Because at 1 atmosphere you heat up dry ice, it's going to go straight to a gas. But if you go above 5.1 atmospheres, you can melt CO2 into a liquid. And then the liquid will boil at some higher temperature. This O here represents the triple point. The triple point is where the solid, liquid, and gas phases meet. And actually, right at the triple point, all 3 phases can coexist. On any of the lines, 2 phases coexist. So when you're melting it, you have the solid and liquid in what we call equilibrium. On this line, we have the liquid and gas in equilibrium. Here we're going to have the solid and the gas in equilibrium. This is another curve here. This is what we're going to do. We're going to hold the temperature constant and then increase the pressure. If we hold the temperature constant and increase the pressure, let's start off with the gas. As the pressure of the gas increases, it should liquefy. But if we're beyond the critical temperature, it never liquefies. It just turns into a supercritical fluid, a cross between a gas and a liquid. Here, if I go from this temperature up, I start off with the gas and then I go straight to the solid. Do you know what going from a gas to a solid is called? It's the reverse of sublimation. What's the reverse of sublimation? Deposition. It's called deposition. We could see lots of deposition in iodine. Do you see all the deposition on the inside walls? So it's going from solid to gas and then depositing crystals on the wall. One of the applications, and you can look this up, there's animations of this, decaffeinating coffee. Rather than using organic solvents like you smell that? You want your coffee soaking in organic solvents to extract the caffeine? Nah. Not me. And then I'd much rather have like supercritical CO2 or something like that extracted, and then be done with it. Water has a very interesting phase diagram because there are multiple solid phases of water. There are high density ice phases. And so we have ice 1 and then much higher density, because as the pressure increases, it collapses the crystal, right? Compresses it. The crystal is quite open. airy and not so dense. But here it collapses it. Actually, not airy because air doesn't go in there, but a lot of empty space. And so we could have different phases of the ice. But another thing is this. Do you see the melting point curve here? It's angled at a negative angle, which means this. Higher pressures favor what phase? Ice or liquid? Normally when you think about high pressures favor solids. Normally. So here, how can we see? High pressures favor solids because as the pressure increases, the solid grows. Here, as the pressure increases, the solid area shrinks and the water area grows, meaning that at high pressures, what's more favored? Liquid water or ice? Liquid water. And so what we could do is we could just pinpoint at what pressure would ice melt. And so if you apply pressure to ice, it'll melt into liquid water. So I don't know if I gave this. Normally I assign the ice skate problem in the homework, where you calculate the pressure of the blade of an ice skate and determine its the melting point. You know, and so with the blade of an ice skate, you can melt the ice just on the surface. Reduce that friction. Maybe I didn't assign it, but water is interesting in that sense. So we have melting, freezing, vaporization, condensation is the reverse of vaporization, sublimation, and deposition is the reverse of sublimation. And then this is our lab today. You know, do you recognize this crystal here? Probably not, but look at each atom and tell me what do you think the hybridization is of this one? sp3 tetrahedral. This is diamond. All the carbon atoms are sp3 tetrahedral, but they don't show all the bonds. You know, they show just this one unit of the crystal here. This is graphite here. Can you see what hybridization all the carbon atoms are? sp2. All the p orbitals are perpendicular to the plane, right? And all the p orbital, what do you think about the pi bonding electrons? Are they delocalized over that sheet of graphite? Yes, they are. In fact, graphite is what we call an anisotropic conductor of electricity. It conducts in two dimensions very well. It conducts in the x and the y, but it does not conduct in the z. It's an insulator in the z. And so graphite's an excellent conductor of electricity. Most covalent, both of these are examples of covalent solids. Most covalent solids aren't good conductors of electricity. And so covalent solids all have strong covalent bonds holding the particles together. This is a cross between a covalent and molecular solid. If you look at a sheet, there are sp2 carbon sigma bonds and pp pi bonds. But if you look between the sheets, then we just have dispersion forces holding the sheets together. And so graphite's used as a high pressure, high temperature lubricant because it can withstand high pressures and the sheets slide on top of each other to provide lubrication. And so this is a very good high temperature, high pressure lube. Graphite. But we're going to look. This is another allotrope of carbon. These are the buckyballs. Have you heard of buckyballs? Allotropes are just different forms of carbon. And these buckyballs here have a very interesting shape. Looks like sp2, but it's not trigonal planar here. See that? But anyway, these buckyballs have some interesting properties, and they have bucky tubes and bucky, a whole bunch of stuff. This is a bucky nanotube. It's very interesting. There's, you know, they're saying, I was reading an article about graphite, graphene. Graphene is the molecule of this here. they're saying they got it like a piece of Scotch tape, and we're able to peel it down to one layer of graphene. It's amazing, just one atom thick. So I thought that was impressive. Well, we're going to look at solids today. So what I'm going to do is I'm going to skip this for now and then jump to chapter 13. We're going to do a lot of these things in the lab. But before I do that, let's talk about some of the solid
Yes.
types of solids. We usually characterize the solids depending on the bond type that holds them together. And so in metals, we have metallic bonds holding them. Metallic bonds can be thought of in two ways. This is called the electron C model, where you have cations and delocalized valence electrons floating around. And since electrons are totally delocalized, they conduct electricity quite well. We call them metallic bonds. The hardness varies from very soft to very hard. Like sodium metal is very easy to cut with a butter knife. You know, and in fact, that's what I used to use, was a butter knife to cut sodium. It worked quite well. Whereas other metals are extremely hard, like tungsten. You know, is quite hard. And the melting points vary from very low, like cesium will melt at room temperature almost, whereas tungsten melts at extremely high temperatures. Platinum, extremely high temperatures. They're all fairly ductile, which means, ductile means draw it into wire. Malleable means shape them to different forms. They're all very ductile, malleable, because the bonding isn't very directional. You know, you don't have these sp3, 109 degree bonds that you have to maintain. And they're lustrous, you know, because of the electrons. And they're good conductors of heat and electricity. Then we have ionic solids, you know, cations and anions held together by electrostatic attractions called ionic bonds. These are hard with high melting points. They aren't good conductors as solids, but they're good conductors as liquids. And a lot of them are soluble in polar solvents like water. So they're highly polar. Network covalent solids would be like diamond, you know, atoms held together by covalent bonds. Most are very hard and either sublime or melt at very high temperatures. Most are non-conductors of electricity. So diamond, graphite, silicon carbide, aluminum nitride, silicon dioxide, which is called quartz. Molecular, so we have the nonpolar. Nonpolar molecules are only held together by dispersion forces. And so soft, extremely low to moderate melting points depending on the molar mass. Actually, some of these melting points can get quite high, like asphalt. You know, if the molecules get quite big, a lot of electrons. Sublime or decomposed. You know, some of these don't melt, they just start to decompose in air. Polar, like ice. Actually, no, polar wouldn't be like ice. Polar would be like acetone, solid HCl, solid acetone, methylene chloride. Excuse me, not methylene, chloroform. Chloroform, that's called. These are held together by dispersion and dipole. Hydrogen bonded ones are held together by hydrogen bonds and dispersion. That's missing. I wonder why they didn't put dispersion here, but they put it up here. Well, dispersion also. But dispersion isn't so significant in something like water and ammonia. Low to moderate melting points, you know, soft, etc. Ice, you know, ice's melting point's not so high. 0 degrees C. All right, chapter 12. Let's just have a brief overview of chapter 13. I wanted to see. Yeah.
Is the cast materials stuff that you teach today or
Yes.
today?
Yes. Test material.
So today's going to be part of the final.
Part of the final.
That's tomorrow.
No, tomorrow's not going to be. But you know, how in depth you need to know it. You just need to know some of the terms and some of the concepts. Like here, you know, solute and solvent. Do you know those? Molarity. Yeah. And so, chapter 13, solution terminology, concentration like molarity, intermolecular forces in the solution process, solubility of gases, vapor pressure of solutions, and then these are called the colligative properties here. And so this is just applications of some of the intermolecular forces that we've been talking about. Solutions are homogeneous mixtures. This is chapter 1, right? But solvent is usually the major component. Solute is the minor component.
You put the solute into a solvent.
Yeah, you put the solute into the solvent. Here's some common solutions. All the solutions don't have to be liquid solutions or aqueous solutions. We have air. Air is a solution of gases, nitrogen, oxygen. Natural gas contains methane, ethane, several others. Liquid solutions like seawater, which are vinegar, soda pop. Solid solutions, yellow brass, which is copper and zinc. Palladium and hydrogen, which is a solid and gas. Hydrogen dissolves in palladium, surprisingly enough. It fits into the gaps in the crystal structure of hydrogen. In fact, the density of hydrogen that you can get in palladium is greater than the density of liquid hydrogen. And so in other words, if you liquefy hydrogen, you get a certain number of grams per milliliter. If you dissolve the hydrogen to palladium, you get more grams of hydrogen per milliliter, surprisingly enough, so it packs it more efficiently. Well, concentration, you guys are familiar with the mass percent, right? Mass of solute over mass of total, or mass of component A. This is like the percent sulfate. You know, grams of sulfate over grams of total. And so we've dealt with mass percent. Volume percent, same thing. Milliliters of whatever per total milliliters times 100. We also have mass to volume percent, you know, grams dissolved. In fact, solubility is often given as a mass to volume ratio. Here's another one that's mass to volume, isotonic saline. Isotonic means the same concentration. Tonic is concentration. And saline is a salt solution. And so isotonic saline has the same kind of, what they call the same kind of osmotic pressure as your blood, which is important because if you don't take, let's say, isotonic saline into your blood, what happens is the blood cells can shrivel up or the blood cells can expand and grow, you know, as water goes into the blood cell or water gets sucked out of the blood cell, depending on the concentration of the salt solution. And so since this is isotonic, it doesn't change the volume of the blood cell. And so it turns out it's 0.9% sodium chloride mass to volume. So what this means is 0.9 grams of sodium chloride per 100 milliliters of solution. That's a mass to volume. You know, we spent some time talking about parts per million, parts per billion, parts per trillion. I did this early on, right? So I can skip this. Right? We talked about the mole fraction, pressure fraction, volume fraction when we were talking about gases. It's the same thing. All the mole fractions have to add up to 1. In other words, all the mole percentages have to add up to 100%. We talked about molarity, moles per liter. We didn't talk about molality. Molality is more hassle. It's the amount of solute in moles divided by the mass of solvent in kilograms. You should know this definition. The advantage of molality over molarity is
Temperature.
Temperature,
One is
right.
temperature.
Good memory. It's because molarities are temperature independent, molarities are temperature dependent. So molarities will fluctuate with temperature. Right. You don't want that sometimes. But molarity is so much easier in stoichiometry. This is called the solution process, the energetics of making a solution. When we make a solution, you have to break apart the solvent molecules to make room for the solute. And that costs energy. That's endothermic. So we break solvent molecules apart. We have to break solute molecules apart to get them to dissolve. And then we mix them. We have three scenarios where we mix. Mixing is highly favorable. That is, the solute-solvent interaction is stronger than the solvent-solvent and the solute-solute. So if the solute-solvent attraction is more favorable, net we get exothermic. The solution should form. The other scenario is if the solute-solvent has the same energy as the solvent-solvent and the solute-solute. You know, when this happens, we form what's called an ideal solution. Did I ever show you what an ideal solution is?
Professor, can you say what molality is again?
Molality is moles of solvent per kilogram of, moles of solute per kilogram of solvent. This is an example of an ideal solution. This I'm going to call the solute, this is I'm going to call the solvent. So when I pour this in here, I have to break apart the interactions holding the solute together, break apart the interactions holding the solvent together to make room, and then I establish new solute-solvent interactions. And so this is water plus water.
That's ideal.
That's ideal. Do you expect any energy changes? No, it's ideal. So it's going to mix easily. Ideal solutions mix. Is there a limit to how much water I can add to water? There's no limit. You know, when something has no limit, it's called miscible. And so what else is water like? Methanol. Methanol and water mix ideally in infinite proportion. So there's no limit. You can mix as much methanol as you want in water until you barely have any water and it's practically pure methanol. Ethanol. Ethanol is miscible. Acetone. Miscible. Miscible means it mixes in all proportions. There's no solubility limit. Whereas if I tried to mix like butanol in here, you know, there's going to be a limit to how much butanol I can get in there because butanol is becoming more hydrocarbon-like. Yeah. Now, what happens in this scenario? In this scenario, we're breaking strong, and we're forming weak. Does that sound favorable to you? No, this is not favorable. This is endothermic. And so you would expect that not to happen. But, well, here's what, these are the things we're breaking. You know, breaking, forming. Ideal solutions, you know, where delta H is equal to 0. Delta H is the solution formation process. So this intermolecular force break, this one break, and form this one. Would you expect these two to mix ideally? This is benzene and toluene. Are they similar or dissimilar? They're similar. In fact, these have no problem mixing. They're very similar. They both have a benzene ring. This one just has a methyl stuck instead of a hydrogen. But methyl is similar in terms of, you know, electronic environment. How about this? You know, chloroform and acetone. Well, the chloroform acetone, is this a hydrogen bond here? This is not a hydrogen bond because the hydrogen is actually bonded to carbon.
Just being attracted.
Yeah. But you know, this hydrogen is actually quite positive. Why is that?
Because of the chlorine inductive effect.
Yeah, inductive effect of the chlorines. So this is dipole-dipole interactions. This, here, breaking apart chloroforms cost energy. Breaking apart acetones cost energy. But the chloroform acetone intermolecular force is stronger than what you're breaking. Therefore, it's exothermic. So this is favorable. We should be forming something that's more stable. Right? It's exothermic.
Would it be ideal?
Ideal is no change. They mix ideally. This, however, isn't so great. This is acetone with, what's this, carbon dioxide? No, carbon disulfide here. This is sulfide. And what happens is if delta H of the solution is too big, we call these immiscible. Did I tell you what immiscible is? They mix in all portions. What do you think immiscible means? They don't mix. Oil and water. Oil and water are immiscible liquids. And so if the delta H of the solution is too great, like oil and water, nothing's going to happen. Water would rather stay with water than pair up with oil. But if the delta H is just slightly above 0, it happens. Now, that's because there turns out to be two driving forces in nature, which we'll talk about later. But one thing nature likes to do is minimize energy. But that's not the only thing, because nature also likes to maximize something called entropy. Entropy is a measure of disorder. And so when you're forming these solutions, we're creating more disordered systems. And that's a driving force in nature. It goes towards disorder rather than ordering itself. So this is an example of slightly endothermic, because here we have to break apart the ionic bonds. Is breaking apart the ionic bonds easy to do? No. You know what the melting point of sodium chloride is, like 700 degrees C, more. That means these bonds are strong. How's a water going to come and pluck a sodium ion off there? Well, typically there's got to be a collision. Maybe it knocks it off, and once it knocks it off, then the water's surrounded. When the water's surrounded, you know what this is called? This is called a hydrated or solvated ion. Hydrated and solvated ions are somewhat stable because of the ion dipole attractions. Ion dipole attraction. In fact, some hydrated ions are exceptionally stable. What do you think are exceptionally stable? The small, high charge density, or the big, low charge density? Small, high charge density, because they can set up more stronger ion dipole interactions. And so things like lithium ion are very well hydrated. But this is why there is a disconnect in the redox table. What's the strongest reducing agent on the chart? Lithium. You wouldn't expect lithium to be, because potassium has a much lower ionization energy, so potassium should be, or cesium should be, right? It turns out that potassium and cesium are much more violent in reaction, but lithium in the long run releases more energy, and that's because of the stability of the product. What happens is hydrated lithium ions are exceptionally stable because they're so small, and they can form these very stable hydration spheres like this. But getting back to these hydrated ions are fairly stable too. So what turns out to happen is we break this apart, we break apart the water molecules, but we form these ion dipole. And so what happens is cost us energy, and then we get energy in return. But the amount of energy we get in return is just slightly less than the amount of energy input. It's like plus 7 kilojoules. So where's that plus 7 kilojoules coming from? Because that's plus 7 kilojoules, we're going from lower energy to higher energy. It's not much, plus 7 kilojoules per mole. But nonetheless, what drives this, because sodium chloride is quite soluble, what drives this is entropy. And so if the energy is not too unfavorable, entropy can drive it. So, plus about 5 kilocalories per mole. I have to convert that. But, you know, it's just slightly endothermic, the whole process of dissolving sodium chloride. What gets it over the hump? What gets it over the hump? Entropy. Entropy. Okay, what is delta G? Delta G is Chem 1B. Delta G, you know, how do you quantitatively account for entropy? Right? We know how to quantitatively account for energy, delta H and delta U. But we want to quantitate for entropy. Well, we need delta G. But delta G is not discussed in Chem 1A. It's Chem 1B. So when we form a solution, this is like vapor pressure, the same thing. We're going to saturate the solution. We aren't saturating airspace. We're going to saturate the liquid. And so when we put some crystals in here, then we have this. Do you know what this process is called when the crystals dissolve? It's called dissolving the crystals or dissolution. And so we have dissolution occur. And then the concentration of ions or molecules or whatever you have in here increases. As it increases, then there's a chance that those ions or molecules can strike and stick. If they strike and stick, that's called the opposite of dissolution, crystallization. And so we have dissolution and crystallization occur. When we've reached the solubility limit, solubility is when it's become saturated. This is a saturated solution. We can't dissolve anymore. And that is the dissolution rate is equal to the crystallization rate. And so it's interesting. If you have a saturated solution with crystals down here, the crystals are changing with time if you watch them. You know, because the old crystals are dissolving, new crystals are constantly forming. But the total mass of crystals stays the same, and the total concentration of the solution stays the same. So this is an example of a dynamic equilibrium. Dynamic because crystallization and dissolution don't stop. Equilibrium because the concentration and then the amount of solid never change. All right, what happens if you increase the temperature? This is solubility here, you know, how much you can get in max. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent. So as you increase the temperature, what happens? It increases solubility. Except for one of them, here. If we increase the temperature of this one, the solubility actually decreases. And so most of these must be endothermic, except for lithium sulfate must be exothermic. Sometimes forming crystals isn't so easy. Because when you form a crystal, you know, everything has to line up perfectly. And so sometimes the nucleation process is sluggish. And so what can happen is we cool it down. Let's say we dissolve this much, 50 grams of KNO3 in there. KNO3 is more tricky because nitrate, do you know what the shape of nitrate is? Trigonal planar. So you got a trigonal planar ion, and potassium's spherical. And the trigonal planars have to line up correctly, right? It's like a triangle plate. And the triangle plates have to be all perfectly aligned in order to crystallize. And so if you have spherical ions, nucleation is much easier than if you have odd-shaped ions, like trigonal planar or acetate. And so what happens is, sometimes when you cool this down, crystal formation is slow. So what you end up with is a supersaturated solution. Supersaturated solutions, you have too much solute in there. The only reason that solute isn't crashing out is because nucleation is so difficult. And so what you got to do is you add C crystals and then have it crash out, or you just wait and eventually it'll crash out of solution. It's supersaturated. In fact, I've got to show one example of that. Some things are easy to supersaturate. That is, some things have a hard time crystallizing, like sodium acetate is the acetate ion. How about gases? If you increase the temperature of the gas, what's going to happen to all the gas that's dissolved in there? Is this water boiling? No. All those bubbles are air. Air is dissolved in water. And so this is well below the boiling point, but those aren't bubbles of steam, that's bubbles of air. Right. Your fish, if you have fish, aren't going to appreciate that because then they can't breathe. Right? 'Cause there's no more O2. So most gases are less soluble as the temperature increases. This is called Henry's law. Henry's law says, you know, the concentration of the gas is going to depend directly on the pressure of the gas. And so the higher the pressure of the gas, the more you can force into water. Double the pressure of the gas, you're going to double the concentration. This K is a constant depending on what gas you're dealing with and what solvent you're dealing with. This is Henry's law in action. Just keep increasing the pressure, you're going to increase the concentration of the gas in the water. This is Henry's law in action. Is this high pressure gas in here? No. Do you know what this is? This is pure CO2. And so if you have pure CO2, that's like 1 atmosphere of CO2. Now, if you open the cap, well, how much CO2 is in air? Very small amount. And so all of a sudden we went from 1 atmosphere of CO2 to minimal atmospheres of CO2. And so now we have a supersaturated solution. Having all this CO2 in here is not stable anymore. What's preventing it from all bubbling out? Nucleation. You know, and I guess there's some fantastic nucleation devices like Mentos tablets or something like that. Have you seen that? Where people drop like a Mentos in here and get a fountain. It shoots up like 20. Have you seen that? Actually, let's take a quick peek at some supersaturated. Since this will save time if I don't actually demo it. But let's see. Which one? Minute 19, that's quicker. Oh, volume is working now.
Hi, I'm Abby and I'm going
I can't. Maybe not this one, but. Okay, let's fast forward a little bit.
Sure.
I know.
3, 2, 1, go!
Okay. All right, let me show you one other example of supersaturated. Yeah. Another classic example is sodium acetate. Sodium acetate is very sluggish. Supersaturated. I'll just pick the first one here. Let's fast forward a little bit. All right. So how do you get the crystals? Right now the crystals are having a hard time crystallizing. And so one thing you could do is add a C crystal. You think you're going to do. So this is probably a room temperature, but they probably heated it up to get a lot of sodium acetate in there and cooled it back down to room temperature, but it didn't crystallize out as it should have. A little seed. Now there's a little template for the crystals to grow, and so the crystals can grow.
Will that keep on expanding?
Yeah, eventually it's going to stop when it hits the bottom of the beaker because sodium acetate is so soluble. You know, you can dissolve that much sodium acetate in a couple of milliliters of water. I mean, the amount of water is tiny. The amount of sodium acetate you can dissolve in there is huge. It's really weird at high temperatures. Yeah, that's crazy. That's like, it's solid. There's a little bit of water in there. If you were to heat that up, all those crystals would redissolve in like a milliliter of water.
So could you like grab it?
Oh yeah, but the temperature is definitely cold. It's very cold. Sodium acetate's not that hazardous. That's why these guys aren't wearing goggles. Otherwise, I'm not supposed to be showing this stuff. So that example. All right. So those are some examples of supersaturated solutions here.
Break.
Yeah, let's take a break and then.
Can we try to do the lab?
Yeah, go ahead.